So now I am going to show you how to set up the hot rolling problem which I have shared with you. We will start with the ABAQUS standard or explicit model. Now in the part manager we are going to create 3 parts. First I am going to start with the stock. So in this case the stock is going to be 2D planar as we are dealing with plane strain modeling. So 2D planar deformable shell, and I'll take the approximate size as 1000. Say continue, dismiss. Now the first I shall create a rectangular geometry. Remember that due to the symmetry in the problem, we are only going to model 1/2 of the stock. The initial height of the stock is given as 57 millimeters. So here what I'm going to do is create a stock of 500 mm length and 28.5 mm height. Next, I'll trim a certain section of the stock so that the rolling gets initiated nicely. So for that, I'm going to draw the roller. So the center of the roller is going to be at a distance of 500 mm along the x-axis and 461 mm along the y-axis, because the roller diameter is 450 mm. So once the roller has been created, next I am going to go to this auto trim option, and then I am going to remove this part and this part. Now if I say fit to view, now I'll get this as my stock section. Now I press escape and done in order to create the stock. Now if I go to view, image part display options, and then say extra fine, apply, then I see the section in a nice and smooth manner. I say okay. Next I'm going to create the descaler. So the descaler also I'm going to create it as a deformable body because I would like to have a mesh, and then I'll use some interaction boundary condition in order to do the heat extraction. So I'll say the descaler is a smaller part, so I'm going to have the approximate size as maybe 400 mm. Dismiss. So the descaler, I'm going to have it as a rectangle of size 80, 20. Again I press escape and say done. So my descaler has been modeled. Next I'm going to create the roll. So roll, I'll say continue. Now roll, what I am going to do is I am going to create it as a circular shell. So for that I'll have the roll center at 500, 461 and perimeter point as 500, 11. So my rule has been created. Next, the inner point again I am going to create as 500, 461 and 500, now I am going to consider a shell of 21 mm thickness, so or 27 mm thickness, or why don't I take it as 30 mm thickness for easy calculations. So this will be, so instead of the perimeter point at 11, now it is going to be at a height of 11 plus 30, which would be 41. Okay, I'll say dismiss, escape, done. Once again, I can go to view part display options, curve refinement, extra fine. Remember that this is just a visualization thing. So these are my parts. Now I'm going to go to the property module in order to define the different materials that are going to come in this particular analysis. So the properties that I would have to use, what I'm going to do is I'm going to put it on one side and then I'll open this file. Sorry, just give me a minute. All right, why don't we start with the elastic moduli. So I'll go to create. So this is the stock. The density. So first I'm going to enter the actual properties. Later on I'm going to do something called mass scaling. So it is 7.85 E minus 9. Next, mechanical, elastic. I'm entering the elastic properties. So here I'm using the units of Newton for force, millimeter for length, and second for time. So the Young's modulus is 213 mega into 10 power 3 megapascals. Poisson's ratio is 0.33. Now we are going to use temperature dependent properties and I'm going to work with degrees Celsius. So this will be 24 degrees Celsius. Next, Young's modulus is 201 gigapascals for Poisson's ratio of 0.31 at a temperature of 230 degrees Celsius. 193 gigapascals, Poisson's ratio of 0.31 for a temperature of 358 degrees Celsius. 172 gigapascals for a Poisson's ratio of 0.32 for 452. 102 gigapascals for a Poisson's ratio of 0.33 for 567. 50 gigapascals for a Poisson's ratio of 0.33 at 704 degrees Celsius. 43 gigapascals for a Poisson's ratio of 0.35 at 900 degrees Celsius. So these are the elastic properties. Next, for the plastic properties, we'll use strain rate dependence and temperature dependence. You have been provided with a Excel file. So what I need you to do is just simply copy this yield stress as a function of equivalent plastic strain, equivalent plastic strain rate and temperature into ABAQUS. All right, so just copy this particular data for the plastic properties. Next, I would like you to go to conductivity. So the conductivity for the stock is fixed. So it is 30 watt per meter Kelvin. It will be the same in the units that we are dealing with. Next, you go to specific heat. So in here, the specific heat, you are going to choose it as 490 E6 thermal expansion coefficient. So that will be there in mechanical expansion. So this is 1.2 E minus 5. Next, inelastic heat fraction, fraction of plastic work converted to heat is 90%. So that's about it for the stock. Next, we are going to create for the roll. Again, density is 7.85 E minus 9. Next, elastic. Here we are going to use only the property set room temperature. So 213 E3 0.33. Next, thermal conductivity is given as 27 and specific heat is given as 490 E6. Okay. Now, what we have been doing over here is we want to speed up the simulation in explicit dynamics analysis. One way to do that is to increase the density of the material, but to not affect the thermal properties. If we increase density, we will have to reduce the specific heat. Now, what I am going to do over here is I am going to increase density by 1000 times. So I am reducing specific heat by 1000 times. I'll do the same for both stock as well as for the roll. So I am increasing density by 1000 times and I am reducing specific heat by 1000 times. Alright. Next, I'm going to create the section. So I'll first create the stock section. So homogeneous solid continue material is stock, plane strain thickness is 1. So in this case 1 mm. Next I'm going to create roll section, solid homogeneous roll, plane strain thickness is 1 millimeter. Last I'm going to assign these properties to the part. So I'll go here, create section assignment manager, select the stock section, done. Next I'm going to go to the roll. Again select the roll section. At last descaler. I'll do the same as for the, so select the section, select the roll section, dismiss. Now the roll and the descaler are going to be prescribed as rigid bodies at a later point of time. We are not going to worry about it right now. Now in reality, you have been given that the stock is at 13750 mm from the roll and the descaler is at 4500 mm distance from the center of the roll. But to just speed things up in the simulation, we are going to place them close to one another. So what I am going to do is I am going to instance create. I'll create all three instances. Okay. So what I'm going to do is first I'm going to move the stock 500 mm to the back. Instead of 13750, I'm only choosing 500 mm of movement. this is to speed things up initially, and if everything is working fine, we can always redo the simulation for more travel of the stock before it comes to the rolling stage. So the starting point is 0, 0, and then I'm moving it back by 500 mm. Next, I'm going to select this, done. So starting point is this. Then what I'm going to do is I'm just going to lift it up by 29.5 mm. So 0, 29.5 mm. Okay, so this will be my initial state. Next, I'm going to go to the step module. Now remember, this is where the physics is prescribed. So what I'm going to do is I'll create step 1. I'll choose this as dynamic temperature displacement explicit analysis, continue. The simulation will be run for let us say we are going to run it for 3 seconds. Run it for 3 seconds, or more precisely, let's say for 3.1 seconds. Now, nonlinear geometric effects, I'm going to leave it as on. Incrementation is automatic. I don't need to do anything different over here. I'll say okay. Dismiss. Next, in terms of output field requests, what I'll do is I will ask for the solution at 200 evenly spaced time intervals within this 3 seconds, or why don't I say 310. So we are getting the solution every 10 milliseconds, all right? And then you are obtaining the results for this different stresses, strains, displacement velocity, acceleration, forces, reaction moments, and then for this contact pressure, and yeah, so for all the contact stresses, I'll say okay, dismiss. Next, I'm going to go to the interaction module. Now, what we will do is we will first describe the roll as well as the descaler as rigid bodies. So for that, I go to constraint, manager, rigid body. So I'll call it as roll rigid, continue, and then I'll select. Alright, so before we do this, we need to define a reference point. So for that, what I will do is I'll go to tools, reference point. I'll select this as a reference point. Now I'll go to constraint, create, so rigid roll, continue, body, and then edit selection. I'll select the roll, done. Reference point, I'll select this, done. Okay, so that's my rigid body. Next, what I'll do is I'll create a reference point for the descaler, and then again I'll do something similar, rigid descaler, continue, so that's the descaler, and the reference point is this. Okay, fine, all right. Now, all right, so this is for this. Next, what we are going to do is we will be going to model, edit attributes, and in here we will prescribe absolute 0. Since we are working with degrees Celsius, absolute 0 would be minus 273 degrees Celsius. Next, Next, we need to put in the Stephen-Boltzmann's constant. So the Stephen-Boltzmann's constant is 5.67 into 10 power minus 8 watt per meter square Kelvin to the power 4. So in the unit that we are dealing with, this will be this E minus 11. Alright, so this will be the Stephen-Boltzmann's constant. So I'll say okay. So this attribute will be applied at all places. Next, we will go to the interaction property manager, and in here what I'm going to do is I'm going to create initially the stock role interaction. So this I'm going to select it as contact, continue. So there will be two interactions, mechanical and thermal. So first I'll go to mechanical. Then normal behavior is hard contact, allow separation after contact. Next, the tangential behavior, I'll assume a penalty model, and in the data which was provided to you, the friction coefficient between the roll and the stock is 0.25. Next, I'll go to thermal conductance. Now thermal conductance for this roll and stock interface is given as 27,000 watt per meter square Kelvin. In the units that we are dealing with, it will become 27. So the conductance will be 27 when the clearance is 0. It will be 13.5, let's say when the clearance is 2 mm, and it will be 0 when the clearance is 4 millimeters. Okay, so all right. Next, so fine. So this I'll say as okay. After this, I'm going to create. Okay, I'm going to create stock d-scalar interaction. So I'll say continue. Here there will only be thermal interaction. Here the conductance will be 25 when the clearance is 0. It will be 25 when the clearance is 1 millimeter. It will be 12.5 when the clearance is 3 millimeters. 0 when the clearance is 5 millimeters. Alright. So we have this. Next, after that, I'm going to create this film condition. So or we'll come to this a bit later. So first, let me prescribe these interaction pairs. So I'll go to interaction manager, create. So in here, first I'm going to create the stock roll surface to surface contact, continue. So select the first surface, that's the first surface, the master surface. Then the second surface, which is the slave surface. So these are this is my surface which would be interacting. So I say done, and then the contact property, interaction property that I would like to mention is stock and roll. I say okay. Next, I would like to create the stock d-scalar. Again, surface to surface contact, continue. So this, done. And then for the slave surface, it would be this. And this would be stock d-scalar interaction property. Okay. Next, I would like to create a surface film condition. So this is for the convection. So I'll just call it as convection, continue. So what I will do is I will select all exposed surfaces, done, and then we will prescribe a film coefficient. It is given as 85 watt per meter square 85 watt per meter square Kelvin. So in the units we are working with, it will become 0.085. And then sink temperature, that is the ambient temperature, is given as 40 degrees Celsius. So I'll leave this at 40. I'll say okay. Next, I will create radiation. So for this, I'll go to surface radiation, continue. Once again, I'll select all the outer surfaces which would participate in convection and radiation, continue. Emissivity is given as 0.83, so we will stick with that. And ambient temperature once again is given as 40 degrees Celsius, so we will stick with that. So convection radiation is prescribed and the heat loss and other things are prescribed. Dismiss. Next, we will go to the load module. Here we will have to prescribe the initial and the boundary conditions. So why don't we start with the initial conditions? So I'll go to predefined field, create. So I'll say stock initial condition. So for this, we go to initial step, category other, temperature, continue. So the stock is at 1100 degrees Celsius. So this is what was given to you. So I say okay. Next, I go to predefined field, create. I'll say role initial condition, continue. I'll select the role, and then this is at 70 degrees Celsius. So the role is nearly at the room temperature. Next, so this is for the temperature initial condition. Next, let us prescribe the velocity initial condition. So for that, I go to predefined field, create. So I'll call it as stock initial velocity. So I'll go to mechanical velocity, continue. I'll select my stock, and the stock is at 460 mm per second along the x1 direction. So prescribe the initial velocity. So now initial conditions are prescribed. Next, let us prescribe the boundary conditions. So for that, first I'll give the boundary condition for the stock, which would be the symmetry condition. So I'll go to displacement. So this would be stock boundary condition, continue. So I'll select the stock symmetry plane, and then let me go to the step 1. So displacement, continue, the symmetry plane, and the boundary condition is that u2 displacement perpendicular to the plane of symmetry is 0. Okay. Next, I'll give the condition for the role. So they'll say, first I'll say role translation. So for that, continue. So I'll select this, and then basically this u1, u2 are 0. Next, we will prescribe role rotation. I'll prescribe velocity over here, continue, reference point 1, and then the roll speed is given as 820 mm per second. So this comes to, velocities are 0. I don't need to prescribe this. Angular speed is 1.83 radians per second, and it is applied instantaneously, and it is along positive x3 direction. So that is applied. And then I'm going to create like displacement boundary condition for the D scalar, continue. So for the D scalar, I'll select this reference point, and basically all degrees of freedom are fixed. Also, for the D scalar, I'll have to prescribe the temperature. So in step 1, so D scalar temperature, it will always be at 40 degrees Celsius, not just the initial condition, it will always be at 40 degrees Celsius. So I think the initial conditions are prescribed, the initial temperature, initial velocity, and then thermal boundary conditions and the displacement boundary conditions are prescribed. Fine, thermal we can do one more thing, which is the normal heat flux is 0, but that is anyhow the default boundary condition, so I'll leave it at that. Now next we go to the mesh module. So this I'll have to do it by parts. We'll start with the stock. So I'll do seed edges. So I'll select this edge, done. I'll do by number. I'll put 50 seeds on the bottom edge, okay. Then again I'll do seed edges. I'll select this vertical edge here. I'll put again by number. I'll put 3 elements, apply, done. Next I'll go to mesh controls. I will select structured mesh for this particular part. Mesh element type, I'll select the region. So it's an explicit element, linear element, okay. And then I'll use enhanced hourglass stiffness to deal with this hourglass effects. Second order accuracy, I'm selecting it as on, and the element type is a coupled temperature displacement analysis, okay. So explicit, linear, plane strain, quadrilateral, second order accuracy, yes, hourglass control is enhanced. So with this I say okay, and then finally mesh part, yes. Something is not right over here. Let me go back and then see what's wrong. So I'll do mesh, delete part mesh, yes. Seed, edges, maybe I'll go to mesh element type, not sure if that's creating some trouble. The second order accuracy, I'll say no. Coupled temperature displacement, this should not affect it. So seed edges, mesh part, okay, something is not right, mesh, delete mesh part, yes. Seed edges, let me see this side also. I'll put only 3 elements over here, okay. Again mesh controls, let me try this. So oh, it says I want it as quadrilateral only, okay. Mesh part, yes, okay. So fine, so this is a nice mesh, the way I wanted it. Next for the roll, I'll do mesh controls, quadrilateral, sweep mesh, seed edges. So for both of these edges, I'll do by number. I'll do 100 elements, apply, okay. Then mesh element type, again I'll do a couple temperature displacement, explicit, linear, plane strain, enhanced, okay. Then mesh part, yes, so this is done. Last is the descaler. Again mesh, seed edges, it won't matter really right now, so I'll just put maybe 20 along the length, and then edges, I'll select this thing. Here it won't matter, so 2. Mesh controls, so I'll do quad, structured mesh, okay. Mesh part, yes. All right, so now all the parts are meshed. I'll go to job. Now before I move ahead, I'll set the work directory. So in this case, I have mine at D, VR, ABAQUS, HotRolling, okay. And then I will save this CAE file as HotRolling 2D explicit dynamic March 4th 24. And then for the job I'll label it as 2D explicit dynamic continue, okay. And then I say submit. Well, we'll see whether I have done everything right or not. More often than not, a few mistakes are made. So let us see whether all aspects of the problem have been modeled correctly or not. So far so good. So the thermal contact has been defined, but no temperature degree of freedom associated with assembly surface 3. Okay, maybe something to do with element type. So let's go to mesh part. So mesh element type. So here I didn't do temperature displacement, explicit, linear. Done. I think that should do it. The other two were done correctly. So for the analysis to progress, the nodes must have displacement and temperature degrees of freedom. For the descaler, the default element type was a plane strain element, so there was no temperature degree of freedom, so it gave an error. So the analysis is progressing well. We'll wait until it is done before we go and start doing some post-processing analysis. I'm currently running the program on a workstation. I'll show you the workstation specifications. I can do that right away. So we can go to the system information. So this is the machine that I'm currently running it in. So it's a 3.3 gigahertz Xeon processor with 4 cores, and I have got 32 GB RAM on this particular machine. So on this system, it has taken me, so CPU time is not given over here, but it has taken me under a minute to run the code. And the stable time increment, as you can see, is around 30 microseconds. And the total number of time increments is around 1 lakh for this particular problem. So I'll say dismiss, go to the results. So we can go to this. We can see that the analysis has run successfully. I'll first show you some temperature plots. So let me zoom in a bit. Let me position it accurately. I'll go to the frame selector and then we'll do this. So you can see, let me change the contour levels over here. So this would be from, let us say, from 700 degrees Celsius to 1100 degrees Celsius. So you can see that as soon as the stock comes under the descaler, there is some cooling. And then also when the stock is being sort of rotated by the roller, there is some temperature drop which is happening. Okay, so the simulation has gone well. Now all of you know how to extract different parameters, but I'll just show you how to get the roll separating force and roll torque. So to extract the roll separating force, go to XY data, create, ODB field output, continue, unique nodal, reaction force, RF2, elements, edit selection, select this, and then say plot. So you get the reaction force. Over here, the reaction force is about 25 kilonewton per millimeter width of the stock. So for example, if you had 1 meter width of the stock which is being rolled, then the roll separating force will be 25 meganewtons. Okay, that's a massive force. The data is also saved in this XY data manager. You can rename it as whatever you want. So for example, roll separating force. Okay. Next, I can also plot the moment. So for that, I can go to tools, XY data, create, ODB field output, continue, unique nodal, reaction moment, edit selection, select the node, then again I can say plot, and this is the reaction moment. So this is Newton mm per mm. So it will also be Newton meter per meter, and that's a massive amount of torque requirement, which is there close to this some 1.3 into 10 power 6. So once again it is there over here. We can rename it as roll torque. Okay. Okay. We can also look at the surface temperature and the midsection temperature. So in order to look at the surface temperature and midsection temperature, I can go to tools, XY data, create, ODB field output, continue. So I'll select, let us say, the temperature, unique nodal, edit selection. So 1 point on the top, 1 point in the middle, plot. So you can see the midsection temperature is only increasing, and it goes to about 1130 degrees Celsius. The top surface temperature, on the other hand, there is a slight drop due to convection radiation, sharp drop due to the descaler. Again, the temperature starts to rise as the heat from the center of the stock moves towards the surface. Again, when it is in contact with the roll, it drops. After it leaves contact with the roll, it again starts to increase. So let's dismiss. So again, I can go here. There are 2 points. Now I don't know which is which one actually. So we can check this. So this is the midsection. So I'm going to rename it as temperature midsection. Okay. And then there is one more. Oh, the other one got removed actually. I don't know why. So midsection I was plotting. So let me just do quickly. I'll select the top point. So here I'll go and say temperature top surface. Okay. All right. What else would be of interest to you? So you can also look at strains and strain rates. So fine, so you can get all these things, and then finally when you want to export the data, you can go here, select whatever you want to export, setup. So fine, so I'll just call it as HotRolling output.txt, and then I can say apply, and then the output data would be created in the corresponding folder. So this was in D drive, VR, ABAQUS, HotRolling. Let me just do date modified, and here you go, the output data. All right. Fine, so this is about it. So I'm going to stop the recording here. Now before we leave, I'll show you something else. Now if you go to this folder where all the data is being stored, which is in D drive, VR, ABAQUS, HotRolling, and now you would see that along with the CAE file, so let me go to type, So this is the CAE file. There is also a journal file which would have been created here. Okay. Now what I'm going to do is I'm going to open this with Notepad Plus. So fine, so this is the one. Now basically this is a Python code. So what I can do is alright, so in another video I'm going to show you how to basically use this Python code and run it from a command prompt. Right.